Good evening to all of you all. In this video, we wish to see what is the work done by a gas in various processes. In physics, we define work, infinitesimal work, as the dot product of force and the displacement. So this would be the magnitude of the force into magnitude of the displacement into cosine of the angle between the two. Yes. Now, supposing we had a gas in a cylinder in which there is a piston, the gas is at pressure P, and due to the pressure P, the piston, let us say, moves to the right by a distance dx. Yeah. Let the area of the piston, cross-sectional area of the piston, be A. So the force on the piston is going to be P into A, and the displacement is dx, so it would be PA dx. Displacement and the force are in the same direction, so you would have cosine of 0. So the work done dW by the gas on the piston would be PA dx. A dx is nothing but the increase in the volume dV. So the work would be P dV. Yes. If the volume increases, the volume of the gas inside the cylinder increases, the work would be positive. We will take the work as positive. Whereas the gas gets compressed, that is, the piston comes inwards, there will be a decrease in the volume, and hence the work will be negative. So whenever the gas expands, we will say the work done is positive, and whenever the gas contracts, the work done by the gas is negative. So the total work would be integral P dV. Now this integral P dV, from, let us say, the limit should be, say, let us say the initial volume is V1 and the final volume is V2, we can calculate the work done in this process. Now, if we plot a P versus V graph, let us say the graph is something like this, then we are saying that from state 1, where the volume is V1, to state 2, where the volume is V2, let us say we are expanding the gas, and so this is the process. So integral P dV, we know from our knowledge of integration, would be the area under this graph. So the area under the PV graph and the x-axis, which is the volume axis, will be the work W. So this way, by comparing the areas, we can compare work. Now, this process that we are shown by a line, by a curve, okay, essentially means that P is in some way related to V. So we could say PV power x is some constant. This constant could be some C dash, where we can vary x and hence vary the process. Let us try to understand, give various values for x. If you give x as, say, give the value of x as 0, yes, you give the value of x as 0, PV power x would reduce to P equals V power 0 is 1, P equals constant. That means it would be an isobaric process. It will be an isobaric process. If x is 1, then you would have PV equals constant, which is an isothermal process. If x is gamma, you would have PV per gamma as constant, which is an adiabatic process, where gamma is the adiabatic constant, the ratio of the molar specific heat at constant pressure to the molar specific heat at constant volume. So this would be an adiabatic process. Then we have an interesting case where if you take the xth root of this would be p power 1 by x raised to v. P power 1 by x into v is constant, and let us say we put x as infinity. If we put x as infinity, then p power 0, this would reduce to 1, and you will have v as constant. So that would be an isochoric process. So let us see, let us derive a general expression for the work done. We saw work is integral P dV from V1 to V2. So this could be put as integral P can be written as C dash into V power minus X. P is C dash into V power X comes to this side as V power minus X dV. So if you integrated this, you are going to get C dash V power minus X plus 1 by minus X plus 1 V1 to V2, where minus X plus 1, since it is the denominator, it should not be equal to 0 or X not equal to 1. That means this formula is not valid for isothermal process. We will have to find the formula for that separately. Whereas it is valid for all processes, for all values of X, it is valid. Negative values of X also included. So this would now be C dash V2 raised to minus X plus 1 minus X V2 raised to minus X plus 1 minus C dash V1 raised to minus X plus 1 by minus X plus 1. C dash, we can put it as P2 V2 power X. Since PV power X is a constant, P2 V2 power X would be the same constant. So we will write it as V2 raised to minus X plus 1. C dash here, we will put it as P1 V1 power X. And you have V1 raised to minus X plus 1 divided by minus X plus 1. So this V2 power minus X will go off here. It will get nullified and you will have P2 V2 minus P1 V1 by minus X plus 1. Now P2 V2 by, if you consider the gas equation, ideal gas equation, P2 V2 is nR T2 and this is P1 V1 is nR T1 by minus X plus 1. So you can write this as nR delta T, where delta T is the change in temperature, by minus X plus 1. That is the general expression for the work, excluding the isothermal process. So for the isothermal process, how can we find the work? For the isothermal process, PV equals constant. So the work would be integral C dash by V dV. Yes. P is C dash by V, X is 1. So P is C dash by V. This is from V1 to V2. Integral of dV by V is ln V. Ln V, V1 to V2. C dash, the constant is nothing but nRT. When you put x equal to 1, PV equals, and you use PV equals nRT, the nRT becomes the constant C dash. So you will have nRT ln of V2 by V1. That will be the work in the isothermal process. Now, let us make a tabulation of various quantities for each of these processes. So first, let us say X, and this is the process. You would like to take work. We are assuming that work is positive, that is expansion. You would like to see what happens to the temperature. What happens to the temperature T? We wish to see. We wish to see what happens to the internal energy, which is given by NCV delta T. NCV delta U is NCV delta T. So internal energy U is NCV T. Then we are interested in how much is what happens to the heat, whether heat has to be supplied to the gas or whether the gas will reject heat. So we will use the first law of thermodynamics. Q is equal to delta U plus T. We will use this. Then we would like to see what is the molar specific heat C, which is nothing but Q by N delta T. We would like to see what the molar specific heat capacity C is. So let us do this starting from 0, 1, gamma and infinity. So when x is 0, obviously it's an process is isobaric. Process isobaric. We are assuming the work to be positive. So if the work is positive, see the expression that we had for the work here. We have it here at the bottom. This is the work. That is the work for isothermal process. If you use that. So we would like to see what happens to the work. Put x equal to 0. If you put x equal to 0, you have work as nr delta t. You have work as nr delta t. So if work is positive, n is positive, r is positive, so delta t must be positive. So we can say that the temperature increases. So if there is an isobaric expansion, the temperature will increase. Because the temperature increases and internal energy is a function of temperature, the internal energy of the gas also increases. Now what about the heat? What will be the sign of the heat? We would like to know. Well, delta U, there is an increase in internal energy. Delta U is positive. Delta U plus W. Delta U, first law, Q is equal to delta U plus W. W is also, we are assuming it to be positive. So Q is positive. That means there is a heat input. So for an isobaric expansion, you have to supply heat from outside. Then the specific heat capacity. Specific heat capacity, Q is positive, heat input, yes, Q is positive, delta T is positive, so the specific heat capacity will be positive. Let us take x equal to 1. That is an isothermal process. So for an isothermal process, the work is nRT ln V2 by V1. Yes, this. The temperature is constant. It doesn't change in an isothermal process. So the internal energy also will remain constant. It will neither increase nor decrease. What can you say? This is an input. So this is the input of heat. What can you say about the heat? Delta U doesn't change. W is positive. So Q will be positive. So this is again an heat input. So in an isothermal expansion also, heat has to be supplied from outside. What about the specific heat capacity? Delta T, the denominator is 0. So the specific heat capacity would be infinite. Because as you keep supplying heat and the temperature just doesn't change. So obviously the specific heat capacity is infinite. So next is when X is gamma, this is an adiabatic process. So in an adiabatic process, the work will be nR delta T by minus gamma plus 1. Yes, instead of X, we have put gamma. Now, we are saying that the work is positive because it's an adiabatic expansion. Now, if this quantity is positive, the denominator is negative because gamma is greater than 1. Yes, it is for a monatomic gas it is 1.67, for a diatomic gas it is 1.4. So gamma is a quantity which is greater than 1. So this denominator is negative. Therefore, the numerator also must be negative. So delta T is negative. That means the temperature decreases. So in an isothermal, in an adiabatic expansion, the temperature will fall. We know Q for an adiabatic process is 0. That is how it is defined. There is no heat input or heat rejection. So Q is 0. So if Q is 0, now see W is positive. So delta U has to be negative, which is of course the case. As temperature decreases, the internal energy must decrease because internal energy is a function of temperature. What about the specific heat capacity? The specific capacity Q is 0 and there is a change in temperature delta T. So specific heat capacity is 0. Now for when X is infinity. When X is infinity, this is the case of an isochoric process. Volume is constant. So if you put X as infinity, work would be 0. As expected, because the gas is neither expanding nor contracting. Volume is constant. Therefore, the work is positive, is 0. Now the work is 0, the temperature may increase or decrease depending on W is 0, so Q is equal to delta U. If you have supplied heat, if heat is positive, then the temperature will increase. That is, if there is a heat input, temperature will increase, internal energy will also increase. If heat is rejected, if heat is taken out, temperature will fall and internal energy will also decrease. The specific heat capacity would be positive because when Q is positive, yes, delta T is also positive. So positive or positive will be positive. When Q is negative, temperature decreases. So delta T is negative, negative, negative. This will be negative. Now, we wish to see the specific heat capacities for intermediate values. what is the specific heat capacity for intermediate values between 0 and 1, between 1 and gamma, between gamma and infinity? What are the specific heats? We would like to see this. So, let us use the first law. The first law says dq is equal to du plus dw. Yes, or you have q is equal to delta u plus w. Q is nc delta t, nc delta t. U is ncv delta t, and w, we saw the work done in any general process was nr delta t by minus x plus 1, except for isothermal, x not equal to 1. So n and delta t cancels, and you have basically Cv can be written as R by gamma minus 1. Cv is R by, from the Mayer's relation, Cp minus Cv is equal to R, and Cp by Cv is gamma. Combining the two, you get Cv as R by gamma minus 1, and here you will have plus R by minus x plus 1. So if you combine this is going to be R gamma minus x, the numerator, gamma minus 1 into minus x plus 1. Okay. Now let us see the ranges. In the range 0 to 1, what happens to the, how is the specific heat capacity? So we would like to take the various ranges, x varying from 0 to 1, and we would like to see each of these factors, gamma minus 1, gamma minus x, and minus x plus 1, what signs these take, and hence what is the sign of C we would like to see, and we would also like to know what is the sign of delta t. Okay, we would like to know what is the sign of delta t, and hence what is the sign of Q, which is nc delta t. So we are going to take the ranges x varying from 0 to 1, x greater than 1 but less than gamma, and x greater than gamma. So you see this gamma minus 1 is going to be positive in all the cases because gamma is greater than 1. Now let's take this case. X is between 0 and 1. Gamma we know is greater than 1. So here gamma minus x is going to be positive. X is between 0 and 1, so it's less than 1. So this quantity will also be positive. So the specific heat capacity, all the three quantities are positive. So the specific heat capacity will be a positive quantity. Now for the sign of delta T, see we know that the work W is nr delta T by minus x plus 1. So we are assuming that the work is positive. Yes, the gas is expanding. Now x is between 0 and, if x is between 0 and 1, this quantity will be positive. So since the left hand side is positive, the right hand side also has to be positive. Since denominator is positive, numerator also must be positive. So delta T would be positive. If you take NC delta T, C is positive and delta T is positive, so Q is also positive. take the case where x is between 1 and gamma. If x is between 1 and gamma, this quantity is going to be positive because x is less than gamma. If it is between 1 and gamma, this quantity minus x plus 1 will be a negative quantity. The specific heat capacity, one of these factors is negative, will be negative. Let us see this quantity. If you see this quantity, x is greater than 1. Therefore, the denominator is going to be negative. Since the denominator is negative, the numerator also must be negative because w is positive. So, this is negative. So, what can we say about Q? X is greater than 1, so this is negative. So, delta T is negative. Yes. So, Q is going to be positive. And C is negative and delta T is negative. So, Q will once again be positive. Yes, Q is once again positive. Now, let us take the case where x is greater than gamma. When x is greater than gamma, this quantity with gamma minus x will be negative and this will also be negative. Since there are two negatives, C is going to be positive. X is greater than gamma, so the denominator will be negative. So the numerator also has to be negative. So this will be negative. And Q will be negative. Yes. Now, the interesting thing to see here is the sign of Q and delta T. When Q is positive, you're supplying heat and the temperature of the gas increases. Quite understandable. Here in this case, you're removing heat because it's negative, temperature decreases. Quite understandable. But here in this case, you are supplying heat and the temperature decreases. Yes, that is because the specific heat capacity of the gas is negative. Let us try to see these things by a graph. Supposing we plot a PV graph, let's say at this point, if you draw an isobaric process, this would be the isobaric process from V1 to V2, isobaric process. Isothermal process would be a hyperbola. The adiabatic will also be a hyperbola. The isochoric would be like that. Yes. So this corresponds to x equal to 0. This corresponds to x equal to 1. This corresponds to x equal to gamma. And this corresponds to x equal to infinity. Now in this region, we are saying that the specific heat capacity is positive. C is positive. In this region also, the specific heat capacity is positive. Positive. For x greater than gamma. These are regions where x is greater than gamma. Whereas here, in this region, specific heat capacity is negative. So when x is between 1 and gamma, the specific heat of the gas is a negative quantity.